afternoon, everyone. I'm Parth, and with me this is Ayush. We are robotics graduate students from CMU, and we are here to present our final project for the Introduction to Deep Learning course, which is titled VLAD, or VMs for Autonomous Driving. Our project focuses on how vision language models can enhance the safety and performance of autonomous vehicles by successfully navigating out of distribution scenarios while driving. And our other teammates are Arane and Abhishek, who couldn't be here today. So let's move on to the motivation. The core motivation behind our work was the long tail of driving interactions. Current autonomous systems are trained on massive data sets, but still struggle with rare, unexpected, or novel scenarios. This led us to three fundamental questions for this project. First, can we build a system that doesn't need to be explicitly taught in every situation? Second, can a model effectively leverage similar non-identical experiences? And most critically, can vision language models reason about this long tail of driving interactions? If they can, how do we use them for real-time control? We plan to answer these questions as we move forward, but let's start with some examples of the scenarios that we're talking about. Next slide. Here you can see a car comes from the back at a pretty high speed, but the Tesla in this video isn't able to detect it. This is an example of an out of distribution scenario, and this is also one. So in this, it is the construction site. There are cones and people holding stop signs that this is a construction zone, but the car tries to move into the lane that is the construction zone. If we had a reasoning loop, maybe this would have been avoided. So the data set we're using to address this problem is bench-to-type data set. It has high-fidelity sensor data, and in a setup, the state of our vehicle is defined by the car's position, orientation, and the velocity as shown here in the presentation. And right now we're trained on the mini version of the dataset, which has 1,400 data points over 10 scenarios, which is manageable for a course project right now. But our goal is a scalable approach, which is over the base dataset that is over 100,000 images. So moving on to the model architecture, our architecture takes a single camera frame from the front camera, the current speed, and predicts 10 future waypoints. That's 2.2 seconds ahead. We use a frozen vision encoder plus a lightweight diffusion transformer. So first we pre-process the image and run it through Qwen 3VL with 4 billion parameters. A vision language model that gives us 640,000 dimensional features as embeddings. We keep this frozen and pre-compute all the embeddings offline for better speed. So these features get combined with the car's velocity and a diffusion time step, then fed into our policy network. A 4-layer diffusion transformer with only 15 million parameters, which is still subject to change as we keep running ablations. The key to our approach is the diffusion algorithm, and specifically two techniques, which is action chunking and forward reverse noising. So action chunking here allows our model to output a chunk of future actions in a single inference step. This is crucial for achieving real-time closed-loop control, as we only execute a subset of those predicted horizon before re-inferring to the model again. So, and forward and reverse noising here in the training process, we start with a clean action trajectory, add scheduled Gaussian noise, and train the model to iteratively denoise it over 30 steps.
So I can take over and show you some initial results. So we wanted to figure out whether the Qwen model was actually capable of reasoning about these long tail situations, and we did that by basically having the Qwen model drive the car. So we gave it a video set of our car's front camera, and we asked it, hey, output a JSON with the steering angle, the throttle, and the brake value, and give a reason for all of this so that you can drive the car. Then we took this JSON and put it to Carla and had the car drive at that rate. So on slide here in the right, you can see that it has seen the red light, and it has explained to us that we have to come to a complete stop at the red traffic light. And you can see that it has set the value of brake to 1.0, throttle to 0, and steer to 0. So this information exists in the Qwen model. This approach that I just described of generating a JSON, that is of course not scalable. That's extremely slow. You cannot do real-time driving with that. So our whole goal is to try to figure out whether we can take the embeddings from Qwen and have our diffusion transformer do the driving. We did just that on the bench-to-drive dataset, as Parth mentioned, and I have a few key results to show in that right now. So we trained the policy over a very small subset of the dataset for around 100 epochs, and we were able to get the loss to go down. This loss is basically comparing the actual trajectory that the car took in the correct scenario versus versus the waypoints that our diffusion models predicted. So that has been our progress so far. Thank you for hanging on with us. Yeah. Our next steps would be to scale to the full dataset. So we're training on 1,400 samples right now. We will scale to the entire dataset, which is 100,000 plus samples. This includes trajectories in all kinds of long tail situations, in all kinds of weather, night, day, etc. Then we will run ablations. Of course, this is a deep learning experiment, so there are a lot of hyperparameters that we can tune. We can tune how many noising and denoising steps we have in the diffusion transformer, which VLM gives us the best trade-off between speed and accuracy and like behavior in the long tail driving situations. And the third step would be evaluation. How does one actually evaluate how a car did in a long tail situation? The only thing that we can think of currently is I look at what the car did and I judge whether it was correct or not. And the second level would be, of course, to figure out, did it actually go where it was supposed to go? Did it make progress along the route? And did it collide with anything? We plan to continue working on this into our next semester. This is a pretty interesting problem, and the entire team has found it intriguing. So, yep, thank you so much.